Now, okay. I'm sorry, I had to rejoin. Now, can you see the screen?
Yes, sir.
Okay. So we want to first of all look at, yeah, this is on the boundary of omega. Um, that is, let us in the two dimensions. In the two dimensions, if we have any domain like this, uh, any domain omega, the inside part without leaving the boundary, we are defining it as Laplacian of u is equal to f, and on the boundary it is we are taking a Dirichlet boundary condition. Dirichlet boundary conditions. This is the Dirichlet. So the main main goal is to prove the uniqueness of solution of the problem one. This is the problem one. Solution of problem one. Okay. Main thing is to prove the uniqueness. For that, we need something called maximum principle. Okay. For proving maximum principle, this is the A part. This is B part. For proving, we need Gauss um, mean value theorem. And for proving Gauss mean value theorem, we need Green's identities. Okay. So first we'll start with today Green's identities. So what are Green's identities? So this is about two functions u and v. If we have two functions in C2 omega, that is what is C2 is twice continuously differentiable. That is u and v are twice continuously differentiable. That means they are differentiable functions, and their derivatives exist, second derivatives exist, and they are also continuous functions. C2 functions. Then integral, integral. What is the Green's identity? Something to do on the integral on the domain and integral on the boundary. So what should be there? This comes from actually um, divergence theorem. Divergence theorem. What is divergence theorem? It is integral f dot n cap d ds on the surface is equal to del dot f bar, okay, dx on the domain. Okay, this was our divergence theorem, which is like if we have a domain and inside part is the del dot f bar. Del is a del is our del u upon del x, comma, operator, differential operator del u upon del y in the two-dimensional case. And f bar is any vector field. Okay, f1, f2, f bar. So we have the right hand side as this thing, and left hand side is n cap is the unit normal, outward unit normal from the boundary of the domain omega. Okay, so here use the divergence theorem, and what should be taken for yeah. In place of f bar, what we are taking is take f bar is equal to v grad u. V grad u. Take f bar is equal to v grad u. Take f bar is equal to v grad u. Okay, this is a vector because this is like v. What is grad u? Del u del x, comma, v del u del y. This is a vector. This is gradient of. Okay, now substituting what is f bar dot n cap. That is dot product with the n1, n2, or so if you dot, this is nothing but v. So we are when we differentiate, when we dot product with the n cap, what is unit normal vector? This is nothing but v del u upon del nu, where nu is the normal direction, differentiation in the normal direction. Okay, this is um, a notation that we follow, and nu is the normal direction. So this will be f v dot v times del u upon del nu. Okay. And yeah, and now substitute what is gradient of f bar here? Sorry, divergence of f bar. This is del dot. Our vector is this one. So this will be Laplacian of yeah, del dot f bar is what? F bar is v grad u. Okay, so this will be what? V times. So this is like product rule. We have to apply the product rule. V times Laplacian of u plus grad v dot grad. These are two vectors. This is a vector. This is a vector. So dot product. So substitute this in the divergence theorem. Divergence theorem says that on the boundary, it is f bar dot n cap, that is v del u nu boundary integral is equal to on the domain is v Laplacian of u plus del v dot grad v dot grad v, and this is the normal on inside the domain. So this is our Green's identity. Green's identity. Now there are particular cases. A part is take v is equal to 1. Take v is equal to 1. Then what is in the left hand side? Del u del nu ds is equal to v is equal to 1. So constant function v, so this is 0. So we have only integral Laplacian of u omega dx. And for the harmonic functions, v part, for harmonic functions, that is, if Laplacian of u is equal to 0, that is, u is harmonic, then the right hand side is 0. So ds is equal to 0 on the bound. So these are the particular consequences of the Green's identities. So once we have Green's identity, we can prove now using Green's identities, prove Gauss mean value theorem. So yesterday we have introduced what is Gauss mean value theorem. In the 2 dimensions, what in 1 dimension I have mentioned, in 1D harmonic functions are nothing but double derivatives are 0, will imply that u is nothing but a linear function, and if it is a linear function, it is harmonic. So value, take any interval x0, x1, and midpoint is, so value at the midpoint is nothing but the average of values at the endpoints. Okay, that is the Gauss mean value theorem. Value of a harmonic function, value at midpoint is equal to average of values at the boundary. Values at boundaries. Average of values at boundaries. So the, in now in 2 dimensions, take I am taking any point xi and a ball centered at xi and radius r, positive. Okay. What I concluded yesterday was instead of looking at the ball centered at xi, we can translate to this to a ball center origin, the same radius. One can come from here to here. Definition of notation is that radius r centered at xi. This is radius r only, but centered at origin. It doesn't matter if, if we take the average on this ball, surface of this ball, or surface of this ball, because it's only a translation. Measure is same. Measure of this ball is same, and values will matter only in the translation. What I am saying, if we have a u function, we want to say that the Gauss mean value theorem is u xi is equal to integral u of x dx measure of dr psi. This is the average value on the boundary of dr. In particular, boundary Xi, what is the definition? It is point all x such that x from xi is less than r. It's an open ball with radius r and center psi. Center psi. So the boundary of VR, I am denoting it as SR. Is what is the definition? This is all point X such. So this is nothing but the boundary of VR. So now what I am saying is instead of this and radius are right, we are going to translate it to and not only or make it dilate. This is by translation, and we are going to even dilate it to radius 1 center. This is centered. From here to here it is dilation. So we don't need to now the details of everything. Only thing what we are saying is the Gauss mean value theorem, the value at the center is equal to integral instead of boundary function evaluation on the surface of the ball BR xi, we can as well take this is psi plus translation plus dilation dx or d surface measure dsx, and it is one upon what is the WN? What is WN? WN is measure of the unit sphere centered at origin in n dimensions. For us, it is U2. UN is, this is n dimensional unit sphere in Rn. Unit sphere in Rn. For us, it is just W2. In 2 dimensions, it is W2. And what is the measure of W2? Measure of W2 is nothing but it is the circumference of the 2 pi. Unit sphere, so it actually it is 2 pi r circumference circle, but it is pi. W3 4 pi surface of the sphere, surface of the measure of surface area of the sphere. Okay, and so on. we are going to see use the Green's identity Gauss mean value error. Use Green's identity to prove. So use what was the Green's identity? We have seen that when for harmonic functions, u is equal to v Laplacian of u plus grad v grad u. This is on the boundary. This is on the domain. So what we are saying now we are working with only v is equal to 1, and we have Laplace function harmonic functions. So this is 0. So what we have is for harmonic functions in particular we have this is equal to 0. Okay. So now here we are working with we want to prove mean value theorem. So omega is take omega is our PR psi. Okay. With all those translations, dilations, and everything we have, we have now this is equal to and here the outward normal is our radius vector. So we in n dimensions we have r power n minus 1 integral del u del r psi plus rx dsx and mod x is equal to 1. Okay. This integral yet we are not using any this is only integration over the boundary of the boundary of the unit sphere, boundary of the open ball. That is equal to this one. And now apply the mean value theorem, or this is equal to by yeah, this is equal to mean value over the sphere of R. What is this? Now bring the this differentiation outside. So what we have is bringing the differentiation outside. Of the integral u psi plus rx dsx. This differentiation with respect to r, of course, we have r power n minus 1, and we have also the yeah. So from here, we what we are concluding is that this is equal to 0. Left hand side is 0. So the mean value, this is the mean value. The mean value over a sphere SR psi, surface of the sphere, of a harmonic function. Harmonic function does not depend on on r, the radius, because the derivative with respect to r is becoming 0. So this shows that the mean value is, let us call this mean value of a function u, define this as of a function u at a point xi and with radius r. This is the mean value. Of course, we have put w n here and w. Then only it is mean value, the measure, and put the new in the numerator. So this function is independent of r. So when it is independent of r, we have but this converges to this is equal to, yeah. So here we have to use something like you have a function mu, and as r tends to 0, sorry. So what is that we are going to use here is on one hand we have mu functions. What is the convergence of this? This is converging to u. Now, okay, now, okay. So we are proving that. What is that we have to prove? We have to prove the using the Gauss, using the Green's identity. Use Green's identity. What we are doing now is using Green's identity implies Gauss mean value theorem. Okay. So we are almost done, because what we have shown now is the mean values of u are independent of r. Okay, so that shows that when it's a now you take a sequence of now tend r to 0. As we tend r to 0, what we get, this converges to u. So finally, we our mean value theorem is this one. That is 1 upon wn integral mod x is equal to 1 u of xi plus rx dsx. Okay, these are our m functions, xi and r. Now what we are doing is, now these are tend r to 0. Let r, as r tends to 0, what will happen? R tend to 0. What will happen if you shrink the balls? R is equal to 0. This will finally, as r tends to 0, because of the continuity of these functions, and because the differentiation is 0, and this r is going to 0. So what you get is u of xi. U of xi is now independent of r, so you can bring it outside the integral, and this will be the average value, the measure of sx s. So that wn and this wn will cancel, and what we get is this one. Okay, as r tends to 0, we get this is equal to. First, establish that m functions are independent of r, and now as r tends to 0, they then this is converging to this one. So finally, we have proved that the mean value, this is the Gauss mean value theorem. And we have variants of Gauss mean value theorem. That is, we don't have to integrate only on the boundaries or mod x is equal to 1. We can have integrals over even the whole unit ball. That is, so we have variants of mean value theorems. First is um, u belongs to C2 omega harmonic function. Let xi be any point inside the domain and pick a positive number r, then positive number r, such that this ball of radius centered in will be and its closure will be entirely inside the domain. Then what we have conclusion is that the average the midpoint value is equal to wn. Instead of mod x is equal to, we can have less or equal to, but n comes here, u xi plus rx. Okay, we don't have to integrate only on the boundaries. There is a variant which is like this, which will be integration inside the sphere, unit ball. And this is not on the boundary. This is not the boundary integral. And what is the second variant? Second variant is that we don't need harmonic functions. We need subharmonic functions. If we have Laplacian of u is greater than or equal to 0, even if inequality, then if Laplacian of u is greater than or equal to 0, then we have the inequalities here. Equal to 1, and this is Sx, and uxi, and we have n wn mod x less or equal to 1. U xi plus rx x. This is x. Okay. Even for subharmonic functions, we have these two qualities. One integration on the surface, one integration on the whole open whole ball. Okay. So now using this, so how to what is the interpretation of this? We have yeah. What is the interpretation of these two? Yeah. So now use this to prove, use Gauss mean value once we apply this, we will understand what is the what is the actual meaning of this Gauss mean value theorem. Okay, use Gauss mean value theorem to prove the maximum principle. Now first write the statement. We'll write the statement of maximum principle. Statement of the maximum principle is U is C2 function, and this satisfies this inequality inside omega. Then either U is a constant function, constant, or U of X is strictly less than supremum of U of Y, all for all Y belongs to omega. That is the maximum value for all X. What can we, how can we interpret? If you take the maximum value over the inside, take a domain, omega. If you take the maximum value at every point, evaluate U at every point inside the omega. Omega is open, also connected set. That is with the meaning of domain. Okay, it's an open set. The boundary is not included. So if you take the evaluate all U's at these inside values and take the maximum, then for every value of X, this will be strictly less. What does that mean? That what can we say from this? The supremum value, maximum value is not inside. There is, that is, interpretation is maximum is attained only on the boundary of omega. That is the meaning. That is the interpretation of this inequality. So let us prove this using the Gauss mean value. Proof of maximum principle. Proof of so let this value denote, let the value, the supremum value, the maximum value of for all Y belongs to omega is called A. Let this be A. Case 1, that is, if A is maximum value is infinity, then there is nothing, because because U is a continuous function. U is a continuous function because it is given, no, U is in C2. Not only U is continuous, but it is differentiable twice and the derivative is also continuous. Because U is a continuous function, it attains its maximum, and every value is less than infinity only, finite. Every value is finite. So anyway, the inequality is true. Okay? Maximum. So that is Ux is less than less than A, less than the supremum value. Now case 2 is if A is finite. If A is finite, then look at the set of all points X belongs to omega such that U of X is equal to A. This define it as set B. this is nothing but U inverse of the singleton set A. So singleton set is a closed set. All singleton sets are closed sets. So and U is a continuous function. So pullback of closed sets under continuous functions are closed sets. So that means that B is, that implies B is a closed set. Now we'll prove that B is also a open set. B is also a open set. What happens if B is also an open set? B is both open set and closed set. So what should happen? Either B should be empty set, or B should be the whole set, that is whole of omega. What is B? B is empty set, meaning the pullback of this set is empty set, means what is B? What was B? B is U inverse of A, that is points X such that U of X is equal to A. This is empty set. There is no point X such that U of X is equal to A. That means what? U of X is less than A. Okay. There is no point in X inside the domain such that U of X is equal to A. That means U of X is less than A. So that is the second inequality. If what is if U of X is whole of omega, that means all Ux all that is these points in omega where U of X is equal to A are this is the whole set. That means what? Every point in the domain omega is mapped to A, that is U is a constant function. Constant. That's what we want to prove. Either U is a constant function, or it is the this inequality, that is U of X, that is U of X is less than the maximum value. That's what we want to prove. So what is left now is to prove that it is open set. This is where we are going to use Gauss mean value. Once we prove that B is an open set, we are done. That means we have proved the maximum principle. So how to prove a set? This set is an open set. B is n. So we are in this situation. This is omega, and B is a set like this inside omega. Subset of B is a subset of omega. So how to prove something is open set? What is the topological way of proving that something is an open set? We take an open ball, take any point, take any point xi, and take a ball centered on xi, radius r. How to prove the set is open? That we do. Suppose this is a B set. Take any point xi and take a ball centered at xi and radius r. For any point, let xi be any point inside B. Xi be any point inside B, and B R xi should be contained in, if we show that, and if there exists an R, no, if for any R positive, if we show that B R xi is entirely inside B, we are done. Okay. To prove B is open, take any point and we show that we are, let us say that we are for some R, if R is positive such that this is any, if I give any R, we are xi should be entirely inside the ball. Okay. For some, sorry, and some R positive. That means what we have to show is we have to produce a ball which entirely contains inside, produce a ball which entirely contains inside B. That is the meaning of showing that it is open set. Okay. How to show that it entirely there exists an R such that, okay. What is the B definition? What is the B definition? B definition are points. So if X belongs to, I have to show that if X belongs to BR xi, implies UX is equal to A. That's what I want to show. That is the meaning of X belongs to. For every point inside BR, we are proving that it is inside the set B. Okay, that is, let us take a point X in BR. I want to prove that, to prove U of X is equal to A. This U of X, this where this X is inside. So now here we apply the Gauss mean value theorem. That is, we have to show that we have to show that there exists a R positive such that U of X is equal to A for every X belongs to BR xi. Yes. So take R is equal to 1. It will work. That is, we have to show that U of X is equal to A for every X belongs to B1 at xi. So suppose not. That is, there exists a point X0 belongs to B1 at xi such that U of X0 is not equal to A. So, suppose not. What is that meaning? That this is not true for every point. That means there exists a point X0 such that in B1 such suppose not that there exists a point where, yeah, what U of, yeah, this is the one. So from here we get the contradiction to the mean value property. Can you see that? What is the mean value property? Says that But u of xi is what? U of xi is equal to a. Here we have to see the contradiction. Here we have to see the contradiction. But u of xi is equal to a. And here we produced a point where u value at x0 is not equal to a. That means what happens? It cannot be a. A is the maximum value. A is the maximum value. So what we are saying is you produced a point where less than a, which contradicts, because u of the is equal to a, and the inequality what we have, u of xi is less or equal to n upon wn, and u xi plus rx dx, and mod x is less or equal to 1. So in the entire ball, unit ball, we have the average value u xi is less or equal to this thing, and here is one point where it is strictly less than. Or equal to a. So just we have to observe this, why it is a contradiction. We'll conclude this part. We'll see afresh in the Friday's class. We will see why this is a contradiction to the inequality. Why this is a contradiction to this inequality. Okay. Just we have to look at it in a fresh way. Okay. I'm stopping here.
Sir,
Yeah.
please can you upload the chapter related to this of the book?
Textbook, na?
Yes, sir, on the mode.
Yeah. The textbook notes is already there in the home page. I will send the
Yes,
textbook part.
yes, the chapter related to this
This book. Okay.
material.
Okay. The textbook I'll send. Yes. Thank you.
Yes, thank
Thank
you.
you. We'll
Sir,
stop here.
Friday is
Yeah.
no class day.
Pardon me?
Friday is no class day.
Oh, no class day. Friday is no class day. Then Saturday? Saturday we have no. Saturday also not there. So okay, fine. Then we'll meet next week.
Okay,
Yeah.
sir. Thank you.